Have you ever wondered how programmers take our incredibly complex, messy, real world, with people and cars and computer monitors, and somehow translate all of that into clean, logical code? Well, for a huge amount of the software we use every single day, the answer is this really powerful idea called object-oriented programming, or OOP for short.
At its very core, OOP is a way of thinking that's built around one central concept, the object. And an object in code is pretty much exactly what it sounds like. It's a digital version of a thing. And just like things in the real world, these digital objects have two key parts. They have data about them, which we call properties, and they can perform actions, which we call methods. Let's make this a bit more concrete. Think about the monitor you're probably looking at right now. If we wanted to model that monitor as an object in our code, its properties would be things like its size, its resolution, maybe its brand, and its methods, the actions it can take, would be functions like turn on, turn off, or even change brightness. You can see how we're starting to build a little digital blueprint of a real-world thing.
So, that's the basic idea of an object. Pretty simple, right? But the real power of OOP, the whole reason it's been a dominant force for decades, comes from four fundamental principles. You can think of them as the pillars that hold up this entire way of programming.
Now, these four pillars have some pretty fancy-sounding names, but don't worry, there's a great little acronym to help us remember them. AIPE, or AIP, and that stands for abstraction, inheritance, polymorphism, and encapsulation. So let's break down what each of these actually means.
All right, first up is abstraction. The core idea here is incredibly simple, but also incredibly powerful. We hide all the complicated stuff and only show what's absolutely necessary.
And that really gets to the heart of it. The user of an object shouldn't have to worry about how it does what it does. They just need to know what it can do. It's all about creating a simple, clean interface for a system that might be really complex under the hood. Think back to our monitor. When you press the power button, you don't care about the circuits, the capacitors, or the flow of electricity, right? You just want the screen to turn on. That's abstraction. It's the same in code. If we have an enemy object with a talk method, as the user of that object, we just call talk. We don't need to know or even care about all the complex code that's making text appear on the screen. We're totally shielded from that complexity.
Okay, our next pillar is inheritance. And this one is all about code reuse and creating logical relationships between our objects. Basically, it's about not reinventing the wheel every single time.
So you can think of a class as the blueprint for creating our objects. Let's say you've built a blueprint for a general enemy. Now, if you want a more specific type of enemy, like a vampire, you don't have to start from scratch. Inheritance lets your new vampire class, the child, automatically get all the features and abilities from the enemy parent class.
Let's walk through it. First, we've got our base enemy class, and it has a generic talk method. Step 2, we create a new vampire class that inherits from enemy. Boom, it gets that talk method for free, no extra work. But then, and this is the cool part, we can choose to override that method. We can give our vampire its own unique dialogue, like, I want to suck your blood.
Our third pillar is polymorphism, and it's probably the most advanced of the four. The name sounds a little intimidating, I know. It literally comes from Greek and means many forms. And that's a perfect description, because it's all about one action that can take many different forms. What makes polymorphism so incredibly useful is that it's dynamic. It lets the program decide which exact action to take while it's running. So even if we treat a whole bunch of different objects the same way, like telling every single one of them to talk, each one can respond in its own special way.
Let's set this up with a question. Imagine we also create a werewolf class that inherits from enemy, and its talk method says, I'm going to bite you. Now, what happens if we put a vampire object and a werewolf object into the same list, a list of generic enemy types, and then we just loop through that list and tell every single item to talk to? Which version of that method gets called? The vampires? The werewolves?
And here is the magic. When we call talk on that first item, the program checks at that very moment and sees, hey, this is a vampire object, and it runs the vampire-specific method. Then when it gets to the second item, it sees it's a werewolf and runs its method. The same exact function call, talk, produces completely different results depending on the actual object's type. That right there is the power of polymorphism.
Finally, that brings us to our fourth and final pillar, encapsulation. Now, if inheritance is all about sharing code, you can think of encapsulation as being all about protecting it.
It's about creating a protective barrier around an object's data to keep it safe and consistent.
The main idea here is something called data hiding. We really don't want other parts of our program to be able to just reach in and change an object's data whenever they feel like it. I mean, that's how you get nasty bugs and really unpredictable behavior. Encapsulation helps us prevent this by controlling who gets access.
So how does this actually work? Well, instead of making an enemy's health property public for anyone to mess with, we make it private. Now, nobody can touch it directly. If another piece of code needs to either read or change the health, it has to go through specific public methods that we create, often called getHealth and setHealth. This gives us complete control. We could add validation in there, for instance, to make sure health never drops below 0. We've effectively bundled or encapsulated the data with the methods that are allowed to operate on that data.
Okay, so we've covered abstraction, inheritance, polymorphism, and encapsulation. But look, this isn't just a bunch of academic theory. Understanding these 4 pillars is what separates basic coding from professional software engineering. So let's connect all this back to the real world.
Because at the end of the day, all good software starts with a great design. These 4 pillars are the tools that developers use to break down massive, complicated problems into small, reusable, and easy-to-manage components. They're the absolute foundation for professional concepts like software design patterns, and for tools like UML, the Unified Modeling Language, which is basically the architectural blueprint for really complex software.
So it all starts with this one simple idea, the object. But by building on that concept with these 4 powerful pillars, we've created a way to design and build the incredibly complex software that runs our modern world. From the operating system on your computer to the apps on your phone, these ideas are absolutely everywhere. The only question left is, what will you build with them?